In 1995, I said 3 words that I needed to say to survive a room. I am an urban farmer. I said it the way you say something when the saying has to be the thing itself. Not a plan, not a pitch, not a future aspiration, but an identity so fully inhabited in the moment of utterance that the room has no choice but to accept it as real. What came with the words, in the same instant, fully formed, like a blueprint delivered rather than designed, was a system. Fish in a tank. Waste rising through the water. Roots drinking from below. Plants filtering the water clean. Water returning to the fish. Nothing wasted. Nothing imported. Life feeding on death until death becomes life again. Vertical, not horizontal like a field. Vertical, like a building grown upward. Every square foot of airspace converted to food production. In part 1 of this series, I showed you the origin, the 1995 proclamation, the 2005 PowerPoint that documented the system with file metadata that predates the commercial vertical farming industry by a decade, the 7-layer framework, biological loop, spatial architecture, community integration, institutional partnership, manufacturing integration, circular economy, and the invasive species extension that I will come back to. The aquaponic closed loop, the vertical growing architecture, the institutional anchor model. I showed you the gap, 15 years between my documented origination and freight farms, 13 years before Will Allen's MacArthur Fellowship, 9 years before the Valparaiso Master's thesis. The record exists. I showed you what it says. In water. In part 2, I gave you the proof at scale. 9 invasive species: Asian carp, zebra mussels, emerald ash borers, feral hogs, kudzu, cane toads, lionfish, Burmese pythons, spotted lanternfly. Each one analyzed using the elemental opposition principle, each one inverted from ecological destroyer into commercial resource, and each one's output feeding back into the urban farm pod system that started the whole framework. I showed you the chemistry. I showed you the output pipelines. I showed you the economics. I showed you the scientific validation. And I showed you the Cognitive Property Rights Act, the legislative proposal that addresses the legal gap in protecting documented cognitive frameworks rather than just specific physical inventions. Part 3 is the upgrade, not a revision of what came before, an extension. The elemental opposition principle is unchanged. The 7-layer framework is unchanged. The invasive species matrix is unchanged. What has changed? Since I first laid this out, since the industry caught up to the geometry I had drawn, is the engineering toolkit available to apply it. Vertical farming has matured as an industry. LED lighting has dropped in cost by over 90% since 2010. Hydroponic and aquaponic system design has been refined through hundreds of commercial installations, thousands of crop cycles, years of yield data. Automation, sensors, and machine learning have entered the grow room. The materials science for recycled plastic structural panels has been validated. Algae biodiesel production has moved from lab bench to pilot scale. Insect protein aquaculture feed has been validated as a complete replacement for conventional fish meal. The science that was theoretical when I built the framework has become applied. This video is about what the original framework becomes when you apply those tools to it. 6 specific engineering modifications, each one solving a problem that commercial vertical farming has been working around for 2 decades, each one grounded in published science, each one feeding back into the same closed-loop architecture that started in a room in 1995 with 3 words. Let me show you what the upgrade looks like. The industry got the spatial architecture right: multi-tier growing systems, LED lighting, controlled environment agriculture. The fundamental physical structure of vertical farming works. Plenty, Aero Farms, Bowery, Gotham Greens. These companies proved the concept commercially viable. They proved that you can grow food in a warehouse, at density, with yields per square foot that dwarf field agriculture, with water use 90% lower than conventional growing in the middle of a city, 12 months a year, regardless of weather. What the industry did not solve is the energy problem, the protein problem, and the water closure problem. Let me start with energy. Indoor vertical farming is energy-intensive by design. LED arrays running 18 to 20 hours per day represent the dominant operating cost in any vertical farm facility. The best commercially available LED fixtures for horticultural applications convert approximately 40 to 50% of their input electricity into photosynthetically active radiation, the light wavelengths that plants actually use. The other 50 to 60% is heat, thermal waste. In most vertical farms, this thermal waste is managed as a problem. HVAC systems run continuously to extract it, consuming additional electricity to remove the energy that was already paid for to generate it. You are paying twice for the same BTU. Once to generate it, once to remove it. The average commercial vertical farm in the United States spends between 30 and 40% of its total operating cost on electricity alone. This is the primary reason vertical farming has struggled to achieve the cost competitiveness with conventional agriculture that its spatial efficiency should theoretically allow. The food costs too much not because the growing is inefficient, but because the energy model is inefficient. Now the water problem. Municipal water systems are the water source for most vertical farms, even the ones that market themselves as 95% more water efficient than field agriculture, which is true relative to sprinkler-irrigated crops, but still represents a significant municipal water draw at commercial scale. In water-scarce regions, the American Southwest, coastal cities in the Middle East, equatorial developing world urban areas, municipal water is not reliably available, is politically contested, and is increasingly expensive. More fundamentally, the reason vertical farming exists as a concept is to bring food production into water-stressed urban environments. But if vertical farming requires those same environments to provide their primary water input, the solution has reproduced part of the problem. There is a version of this conversation that ends with the conclusion that vertical farming is a technology for wealthy coastal cities with abundant water and cheap electricity, and not much else. That is not a wrong conclusion given the current state of the technology. It is the conclusion this video is designed to obsolete. Now the protein problem. Vertical farming, as commercially practiced, grows leafy greens. Lettuce, spinach, kale, herbs, microgreens. These are high-value crops that can justify the economics of indoor production. What commercial vertical farming has not delivered at scale is protein. Fish, specifically, the protein source that closes the aquaponic loop I designed in 1995 and that Will Allen's Growing Power demonstrated in its Milwaukee facilities. The primary reason aquaponics has been slow to scale alongside hydroponic vertical farming is feed sourcing. Aquaponic fish need to eat. The conventional feed source, fish meal made from wild-caught anchoveta and other small pelagic fish, is a global commodity subject to supply constraints, price volatility, and increasingly severe environmental criticism. The fish meal industry competes with human food consumption for the same wild fish stocks. It is not a closed loop. It is an external dependency that the rest of the system cannot close around. 3 problems, 3 open loops, 3 places where a system that should be self-contained is instead dependent on external inputs that are expensive, environmentally costly, or geographically unavailable. The 6 modifications I'm about to describe close these loops, not partially, not as a future aspiration, based on published science, validated at bench and pilot scale, designed with specific engineering parameters and economic projections. The loops close. I will show you exactly how. Let me walk you through the 6 modifications in sequence. I want to be specific about the engineering, because the specificity is the argument. This is not a concept. This is a design. The first modification addresses the energy and water problem simultaneously with a single piece of hardware. At the base of a 12-foot growing column sits a titanium basin filled with seawater. Above that water, a 1250-watt infrared LED array fires straight down. Not to illuminate the plants, the plant-facing LED arrays are mounted above each growing tier as they are in any conventional vertical farm. This array is dedicated to the basin. Its purpose is to evaporate. The basin water climbs to 65 to 70 degrees Celsius under the infrared array. It does not boil violently. It evaporates, cleanly, steadily, at a rate of approximately 0.83 liters per hour per square meter of basin surface. The vapor that rises from that basin is pure. Every sodium ion, every heavy metal, every microbial contaminant, every dissolved solid stays behind in the basin. What rises is clean freshwater vapor. Critical specification: the 65 to 70 degrees Celsius basin is a sterile evaporation zone. No fish, no algae, no bacteria can survive there. The fish chamber is thermally isolated in a separate compartment at the column base, maintained at 20 to 28 degrees Celsius. The algae photobioreactor spirals the column exterior at ambient room temperature. The living ecosystem never contacts the evaporation basin. The basin is seawater in, freshwater vapor out, concentrated brine purge, nothing more. The fish and algae live in the cascade loop and the fish chamber, not in the still. The energy running this desalination system is not a new line item. You were already paying for it. The LED arrays have to run to grow the food. The heat they generate was already happening. In most vertical farms, it is currently being paid for twice, once to create it, and once to remove it, with HVAC. The stacked still captures that sunk cost and converts it into fresh water. The electricity bill does not change. The water bill goes to zero. At a 10-tower commercial installation, this system produces approximately 187 liters of freshwater daily from seawater, using energy the facility was already consuming. The municipal water connection becomes redundant. In a coastal city, this matters economically. In a water-scarce inland city served by desalinated water trucked in at premium cost, it changes the entire financial model of the installation. The stacked still is a universal water appliance. Identical mechanical specifications whether the input is seawater, brackish water, or polluted freshwater. Built to marine-grade standards, it withstands the harshest inputs and functions identically across all source modes. Source-agnostic modifications. 4. Vapor ladder, drip-down cascade, rotating tiers, sealing heat loop, PTFE vapor seals. These operate independently of input water salinity. They interact exclusively with pure condensed H2O vapor or the physical tower skeleton. Source-dependent modifications. 2. Stacked still desalination architecture and salt byproduct module require salinity for the artisan salt revenue stream. However, the stacked still's purification function works identically on fresh water, only the operating temperature shifts. 55-60 degrees C for freshwater versus 65-70 degrees C for seawater, saving 18% infrared array power, and the purge valve frequency changes. 90% reduction for freshwater, switching from salt harvest to mineral scale flush. Dual-mode facility integration. A single facility can operate seawater and freshwater columns simultaneously with completely isolated fluid loops, no shared drainage sumps or nutrient dosing stations. Cross-contamination risk. Even 1% seawater backup into freshwater columns causes osmotic cell lysis in algae and biochar beds. The infrastructure separation. Dual sump split grid with dedicated marine and freshwater lines. The shared synergy. Energy and gas loops remain fully integrated across all columns. Nutrient supplementation calibration. Seawater track requires heavy potassium silicate and calcium nitrate supplementation to block sodium uptake. Freshwater track switches to chelated iron and magnesium sulfate to counteract lack of natural micronutrient depth. The tower hardware never changes, only the external nutrient stock tanks. Manufacturing. Imperative. 1 standardized stacked still module. No coastal model and inland model. Humanitarian relief groups can deploy the exact same unit to desalinate seawater in the Middle East or strip heavy metals from Flint, Michigan pipelines. The machine remains identical. Only the fluid feeding it changes. Rising vapor has one enemy: unmanaged condensation on the column walls before it reaches the plant tiers. In an unmanaged column, moisture would condense on the structural shell and run back down to the basin without ever reaching the plants. The vapor ladder solves this with a specific mechanical architecture at each growing tier. every 11.76 inches up the column at each of the 10 plant tiers. A 45-degree anodized aluminum condensation ring reaches inward from the column wall, leaving an 8-inch vapor chimney open at the center. Each ring is thermally coupled to the outside world through a solid copper rod that passes through the column wall and connects to a finned aluminum heatsink mounted on the exterior. Room air at 22 degrees Celsius. The ring surface inside the column held at 45 degrees Celsius. Vapor reaches that thermal boundary, surrenders its latent energy to the copper fin pathway, and becomes liquid water, clean, salt-free, at exactly the plant level where it is needed. Physics being physics, the lower tiers condense more water than the upper tiers. Heat decays as it climbs. Left uncorrected, the plants at the top of the tower would receive less water than the plants at the bottom. The correction costs $12. A 2-watt heat-resistant draft fan mounted at the column cap pulls a gentle vacuum through the full column length, drawing vapor evenly through all 12 feet before it collapses. Tier 10 receives within 5% of the same water volume as Tier 1. The entire vapor distribution system, all 10 tiers, the full 12 feet, runs on 2 additional watts of electricity. Now, and this is the question that anyone who has actually worked in a humid indoor grow environment will ask immediately: what happens to the ambient air? The stacked still is generating water vapor inside a sealed column. Most of that vapor condenses at the growing tiers as designed, but not all of it. Vapor escapes at the root zones, at the column base seal, at every access port. 10 columns running simultaneously in a 10,000 square foot facility represent a meaningful moisture load on the ambient air. Without management, the facility moves toward 100% relative humidity, the condition that collapses growing operations through fungal disease, powdery mildew, botrytis, and the structural degradation of everything in the room. This is not a theoretical problem. It is the reason that conventional high-humidity controlled environment agriculture runs large, expensive dehumidification systems continuously. Those systems, refrigerant cycle dehumidifiers running at scale, can represent 15 to 20% of total facility electricity consumption on their own. Adding a vapor-generating desalination system without solving the ambient humidity problem would simply shift the electricity cost from the water bill to the HVAC bill. The solution is in the column architecture, not in the HVAC system. The copper heatsink fins mounted on the exterior of each column do double duty. Inside the column, they are the cold surfaces that trigger condensation at each growing tier. Outside the column, they extend into the room air as passive dehumidification fins. Any water vapor in the ambient room air that contacts a fin surface at 22 degrees Celsius in a room at, say, 75% relative humidity will condense on the fin surface and run down to a collection trough at the column base. No compressor, no refrigerant. No additional electricity beyond the ambient room temperature differential that already exists between the column exterior and the room air. This is not capable of handling the full dehumidification load of a conventional growing operation. Conventional HVAC dehumidification would still be required at reduced capacity, but the passive fin dehumidification across a 10-column installation reduces the active HVAC dehumidification load by an estimated 40 to 60% based on surface area and the temperature differential available in a 22 degrees Celsius grow room environment. The second layer of the humidity management strategy is at the crop level. The specific crops suited to operation inside a vapor column system, herbs, microgreens, baby greens, watercress, are naturally humidity tolerant at high relative humidity, unlike fruiting crops such as tomatoes or peppers, which require lower ambient humidity for fruit set and disease suppression. The crop selection for the pod system is not arbitrary. It is matched to the environmental signature of the production method. High humidity leafy greens inside vapor columns. Lower humidity fruiting crops, if desired, in separate growing areas with conventional HVAC at full specification, but outside the vapor column architecture. The humidity is not a problem to be eliminated. It is a design parameter. The system is designed around the humidity it generates, not against it. The third modification is the one I get asked about most. How do you deliver water to 10 growing tiers without running a pump and solenoid valve to each one? The answer is the drip-down cascade. Gravity-fed, passive, elegant in its simplicity. Water enters at the top tier, nutrient-rich, oxygenated, straight from the fish tanks. It saturates the growing medium at Tier 1. Then it drains through a sealed port, directly to Tier 2 below. Tier 2 receives water that has already been partially filtered by Tier 1's root zone. Tier 2 drains to Tier 3. This continues all the way down the column. 10 tiers, 1 water entry point at the top, gravity doing all the work. The engineering is in the port design. Each tier has a drain port offset from the fill port of the tier below, creating a slight splash gap that re-oxygenates the water as it falls. Dissolved oxygen drops 40% per 3 tiers without this aeration. With the splash gap, oxygen remains above 5 milligrams per liter even at Tier 10. Fish need oxygen. Plant roots need oxygen. The cascade provides it passively, no air pumps required. The answer is in the tier architecture. The LED array mounts on a central recessed hub, sunken into the tier surface, not protruding downward. Around that hub, at the tier perimeter, runs a sealed distribution ring, an annular channel that collects the drain water from the tier above and redistributes it evenly across the growing substrate. The water never passes directly beneath the LED. It flows through the outer annulus, the ring-shaped space between the column wall and the LED housing. The LED itself is sealed with an IP67 rated gasket, rated for continuous high humidity operation. Above the LED, a simple polycarbonate drip shield, a shallow dome, catches any stray condensate and redirects it to the distribution ring. This is not a speculative design. It is the standard architecture for multi-tier aquaponic columns. The water path and the electrical path are physically separated at the design level. The cascade flows through the column perimeter. The LED occupies the column center. They do not intersect. And central electrical hub, yellow icon. The cascade is not just water delivery, it is nutrient staging. But first, the water architecture requires a critical reblending step. The stacked still extracts pure water vapor at 0 ppm TDS, leaving all nutrients and fish waste behind in the basin. The ultra-pure condensate caught by the vapor ladder cannot feed plants directly. It is a blank slate. It gravity drains into a central sump where it is actively reblended with high nitrate water pumped from the fish chamber. This blending targets an optimal EC of 1.2 to 1.6 mNES before entering the drip-down cascade. Top tiers receive water at full nutrient strength, ideal for heavy feeders like dwarf tomatoes and strawberries that need maximum nitrogen and phosphorus for fruit development. Middle tiers receive partially depleted water, perfect for leafy greens that thrive on moderate nitrate levels without salt buildup. Bottom tiers receive lean water, suited to moisture-tolerant herbs like watercress and mint that extract trace ions from low concentration flows. One water input, 10 different growing environments. The cascade creates a nutrient gradient that matches crop needs at each level. The substrate containers, the trays that hold the growing medium at each tier, are injection molded from recycled agricultural waste. Rice hulls, wheat straw, corn stover, bound with food-grade lignin resin. They are not designed to be permanent. After 18 to 24 months of continuous operation, approximately 8 crop cycles, the containers themselves begin to degrade. At that point, they are removed, crushed, and added directly to the compost stream. The biochar substrate inside them, now enriched with root biomass and microbial colonies, is either replanted into new containers or sold as premium soil amendment. The specification: food-grade polyhydroxyalkanoate bioplastic, PHA, derived from fermented agricultural waste. Melting point: 160 degrees Celsius, well above the maximum operating temperature of the column. Service life: 18 to 24 months. End of life: fully compostable under aerobic conditions, breaking down into carbon dioxide, water, and biomass within 90 days in a commercial composting facility. This is not a minor detail. It is the difference between a system that produces waste and a system that produces only product. But there is a deeper innovation here, one that transforms the substrate from a consumable into a cascading resource. Cycles 1 through 3. Primary structural phase. Virgin PHA matrix maintains tensile strength of 25 to 40 megapascals. The composite holds its molded geometry as large structural clumps, 6 to 10 millimeters in diameter. Saturated hydraulic conductivity, 120 centimeters per hour. These clumps are deployed at tiers 1 through 3, the upper levels where water enters the column unthrottled and needs maximum drainage capacity. Cycles 4 through 6. Regrind pellet. Phase. Heat and water exposure trigger hydrolytic degradation. Polymer bonds break. Tensile strength drops by 45 to 60%. The material becomes brittle, no longer capable of supporting large structural shapes, but it can be ground down and repressed into low-density, high-porosity micropellets, 2 to 3 millimeters in diameter. These micropellets rely on capillary suction rather than structural rigidity. They are deployed at tiers 7 through 10, the lower levels where water volume is reduced by upper-tier transpiration and high capillary tension is needed to pull remaining moisture into roots. Cycle 7+. Exhaustion. Threshold. The polymer's molecular weight falls below the mechanical binding threshold. The matrix crumbles under light finger pressure, transitioning into a high surface area soil amendment. This exhausted substrate is removed from the column and sold as premium soil amendment or compost. The material has completed its full life cycle, from structural container to drainage media to capillary sponge to soil fertility. The reprocessing protocol is specific. Step 1. Pyrolytic roasting. Spent substrate undergoes flash roasting at 400 degrees Celsius in a sealed nitrogen atmosphere. This temperature vaporizes root biomass and microbial biofilms into synthesis gas, leaving the PHA biochar composite skeleton intact and sterile. The roast must reach 400 degrees for full sterilization, then stop. End of Step 1. Step 2. Grinding and remelting. The roasted composite is milled into fine powder. The powder is remelted at 160 to 180 degrees Celsius and re-extruded into new pellet forms. PHA can undergo thermal re-extrusion 3 to 4 times. After that, severe macromolecular chain scission occurs. The biochar filler, 20 to 40% by weight, acts as a thermal stabilizer. It absorbs localized shear stress during remelting, and it extends the composite's recycling lifespan to the 6-cycle threshold. Step 3. Cold compaction for later cycles. By cycle 4, the melted polymer behaves less like a thick resin and more like a runny liquid. The melt flow index spikes. Standard injection molding no longer works. Cycles 4 through 6 must switch to low-pressure cold compaction pelletization using a secondary water-based binder like sodium alginate or starches. This is not composting. This is cascading material life cycling. The substrate moves down the vertical column as its structure degrades. Upper-tier drainage block, lower-tier capillary sponge, soil fertilizer, no waste, only product transformation. 4 failure mode diagrams appear. But the cascading substrate architecture introduces 4 failure modes. Failure mode 1, sodium sink effect. Biochar features high cation exchange capacity. If the stacked still experiences a temporary boiling flare-up that splashes trace sodium or heavy metals into the condensate line, the biochar in tiers 1 through 3 will trap those ions. When you grind and remelt that char for cycle 4, those trapped heavy metals lock into the plastic matrix. As the PHA biodegrades in the lower levels, it releases a concentrated burst of those metals straight into the roots of your sensitive lower-tier crops. Mitigation. Implement a strict freshwater flush step during the pyrolytic roasting phase to wash away accumulated salts before remilling. Failure mode 2. Root exudate hysteresis. Plants naturally exude organic acids and hydrophobic phenolic compounds through their roots. These hydrophobic compounds can coat the internal pores of the biochar, permanently changing its water retention characteristics. Mitigation. The pyrolytic roasting cycle must reach at least 450 degrees Celsius to fully crack and vaporize these complex plant-derived oily rings, restoring the carbon's original hydrophilic water-attracting surface. Failure Mode 3. Premature biopolymer collapse via aquaponic bacteria. Your system uses a rich, living aquaponic fish effluent filled with active heterotrophic bacteria. These bacteria naturally produce PHA depolymerase enzymes to break down organic wastes. While virgin PHA resists these enzymes well, by cycle 4, the material's surface area is highly fractured. The active biology in the water may trigger a premature collapse of the pellets mid-cycle, turning your lower tiers into a dense, muddy sludge. That chokes out root oxygen and causes crop failure. Mitigation. Monitor melt-flow index shift after each cycle. When MFI spikes beyond the injection molding threshold, switch immediately to cold compaction pelletization with alginate binder. Do not attempt to remelt beyond the polymer's mechanical binding threshold. Failure Mode 4. Intracellular salt crystallization. The popcorn effect. During thermal concentration steps, trace brine can seep into the micropores of the biochar. When this wet substrate is moved to the 400 degrees Celsius pyrolytic roasting oven, the trapped water will flash into steam instantly. This rapid expansion can cause the salt crystals inside the pores to explode outward like popcorn, shattering the internal microstructural sanctuary needed to house your nitrifying bacteria. Mitigation. Dry the substrate to less than 5% moisture content before pyrolytic roasting. The drying step is not optional. It is the difference between intact microstructure and shattered pellets. The 4 failure modes now shown with their mitigations. Freshwater flush, 450 degrees cc roast, MFI monitoring, pre-drying. The cascading substrate architecture is physically feasible. The degradation pathway is documented. The failure modes are identified and mitigated. The innovation is not speculative. It is a material science specification grounded in published polymer recycling literature and biochar characterization research. Modification 4. Rotating tiers. Access and light uniformity. There is an access problem in any tall, vertical growing column. The higher the tier, the harder it is to reach. Commercial vertical farms limit column height to 6 or 7 tiers, not because of light or structure, but because workers cannot safely harvest above that height. The rotating tier system solves this mechanically. Each tier mounts on a low-friction bearing ring that allows independent rotation around the central column. A small stepper motor at the column base drives any individual tier to a designated harvest position at the front. A worker standing at floor level can reach it without a ladder. Rotation serves a second function: light uniformity. LED arrays mounted above each tier illuminate the surface below. But illumination is not perfectly uniform. The center receives different intensity than the edges. Slow continuous rotation, 1 full revolution every 4 to 6 hours, exposes every part of the surface to the full light profile. In a fixed configuration, center-to-edge PAR variation ranges from 35 to 50%. At approximately 0.003 RPM, cumulative daily light integral flattens to within plus or minus 3% over a 14.5-hour photo period. The yield consequence: 12 to 18% increase in net biomass. Edge plants stop starving. Center plants avoid heat stress. Staggered maturation disappears. Marketability per harvest rises from 80 to 85% up to 98%. Bearing specification: ceramic hybrid slewing ring. Single row 4-point contact, 18 to 24 inches diameter. Static load rating 10 kilonewtons. Rings, grade 316 stainless. Rings, PEEK. Rolling elements, silicon nitride ceramic. Rust-proof. Zero lubrication. Stable at 65 degrees Celsius. Lubrication protocol: none. Drive specification: NEMA 17 bipolar stepper, 1.8 degree step angle, 100 to 1 planetary gearbox. Driver TMC2-209 at 256th microstepping. Effective 5,120,000 microsteps per revolution. Input frequency near 237 Hz at 0.0028 RPM, eliminating harmonics and torque ripple. Motion is imperceptible to plants. Maintenance: 1 annual high-pressure freshwater rinse. Service life greater than 10 years. Any tier to floor level in under 30 seconds. Modification: 5. Sealing heat recycling loop. Heat rises. In facilities with continuous LED operation, the ceiling accumulates warm, humid air. A low-resistance return plenum at ceiling height collects this warm air. It routes the warm air via insulated ductwork down to the seawater basin as supplementary preheat. Pre-warming seawater from 15 to 35 degrees reduces infrared array load by 15 to 25%, cutting 190 to 300 watts per column continuously. For 10 columns, that's 1.9 to 3.0 kilowatts, roughly 3 to 4 megawatt hours per month. Air to water U value 15 to 50 watts per square meter, Kelvin unfinned, 50 to 150 with high-density aluminum fins. The air side controls resistance. Fins are mandatory. Geometry: 8-inch circular double-walled insulated duct. Air velocity 4 to 6 meters per second. Seawater flow 1.5 to 2.5 liters per minute to maximize delta T capture. Greenhouse stratification and heat recovery literature validate the differential. Up to 22% reduction in cooling demand while preheating the basin supply. Modification 6. PTFE vapor seals for rotating tiers. Rotating tiers require a seal that maintains vapor containment while allowing continuous slow rotation. The solution borrows from industrial rotating shaft seals. Each bearing ring carries a PTFE lip seal riding on a hard anodized aluminum track. Friction is minimal at rotation rates of 1 revolution per 4 hours. Drag impact is negligible. A secondary labyrinth seal surrounds copper heat sink penetrations, a tortuous path that dissipates pressure without moving parts. At 60 to 65 degrees Celsius and 90 to 95% relative humidity, PTFE vapor permeation is effectively zero, below 1 × 10 to the negative 11 grams per meter squared per second per Pascal. Any bypass depends on surface finish. The track must meet raw, weighing 0.4 micrometers. Friction torque at required speed is between 0.15 and 0.45 newton meters. A high torque microstep drive consumes under 5 watts continuously. Service life: 20,000 to 45,000 operating hours, roughly 3.7 to 8.5 years before inspection or replacement. Section 4. The economics. Baseline: a 10,000 square foot vertical farm with operating costs of $12 to $18 per pound of leafy greens. Annual electricity: $280,000 to $350,000. Modification 1. Water cost elimination: $18,000 to $36,000 saved annually, coastal; 80 to 90% draw reduction inland. Modification 2. Passive humidity management reduces active dehumidification by 40 to 60%, $16,000 to $42,000 annually. Modification 3. Drip down cascade eliminates tier-level pumps and valves, $3,000 to $5,000 hardware per column up front, $2,000 to $4,000 per column annually in electricity and maintenance. Modification 5. Ceiling heat recycling, $400 to $500 per month electricity saved, plus up to 22% HVAC cooling reduction, $8,000 to $15,000 annually. Modification 6. PTFE vapor seals and rotating access, 15 to 20% harvest labor reduction, $12,000 to $18,000 annually per 10-column installation. Aggregate improvement, roughly $90,000 to $150,000 improvement per year. Variant note: $110,000 to $190,000 range across sites. Aggregate improvement, roughly 15 to 25% better operating cost structure. Break-even moves from 42 months to 22 to 28 months. The byproduct most people miss is salt. Monthly purge and dry yields about 200 pounds of thermally crystallized sea salt. At $7 to $12 per pound wholesale, that's $1,400 to $2,400 per month. Register under FDA Bioterrorism Act. Implement FSMA CGMP and HACCP. Test per food chemicals, codex, sodium chloride content, heavy metals below thresholds, microbial panel clean. Qualify as non-synthetic, non-agricultural ingredient under CFR 205-605 AA to enter organic supply chains. Industrial precedent exists. The Stacked still brings it to facility scale with provenance, crystallized by the same lights that grow the food. Every component rests on published science. The integration, 6 modifications unified within the 1995 framework, is the innovation. The record exists. In 1995, I said I am an urban farmer. The words rearranged the room. They became an assignment. 30 years later, desalination on waste heat, gravity-fed cascade, rotating tiers, sealing heat loop, vapor seals. A facility growing its own water, climate, access, and efficiency from physics it was already paying for. Life kills death. At every scale. The system is complete. The record exists. What comes next is up to you. But a system documented is not a system built. The 15 engineering queries answered here are the research foundation, not the build. Workshop bench, CPVC. Workshop bench, titanium. Workshop bench, extrusion. Workshop bench, PTFE. Workshop bench, copper rod. Workshop bench, stepper. Workshop bench, bearings. Part 4 is the prototype build, a 12-foot column, 10 tiers, titanium basin, vapor ladder, drip-down cascade, rotating tiers with PTFE seals. Sealing heat loop, algae photobioreactor, fish chamber with lift, hands assemble, first water, LEDs. Fish introduced, sensor streaming. Performance will be measured, freshwater rate, par uniformity with rotation, nitrification at elevated temperatures, LED reliability, yield comparisons, economics, including salt revenue, 1 column to 10 to 20, to facilities in multiple cities. Part 4 is not about what could work, it is about what does, because it is built. The system is documented, the specifications are complete, the build is next. Part 4, the prototype build.